We've talked about how quantum computers are enabling extraordinary use cases now, long before the machines will threaten cryptography. Some of these applications can even help companies protect against immediate security threats and vulnerabilities. We explore one such exciting experiment, along with some other hacker goodies, in this episode of the Post-Quantum World. I'm your host, Konstantinos Karagiannis. I lead quantum computing services at Protiviti, where we're helping companies prepare for the benefits and threats of this exploding field. I hope you'll join each episode as we explore the technology and business impacts of this post-quantum era. Our guest today is the CTO and co-founder of Quantum Village, Mark Carney. Welcome to the show.
Thank you very much. It's lovely to be here. Thank you.
Yeah, this has been brewing for a while. We met at IQT in New York.
That's right, yes.
Yeah, we had a little chat. And yeah, there's some good stuff coming in the future, which we'll get to. But first of all, I like to ask this sometimes. Just give us a quick intro to how you got started in quantum, because a lot of our listeners are new to it, or
Yeah, so I am a mathematician by training. Well, actually, I was a violinist once upon a time, and I was...
Same thing.
Yeah, same thing. It's all just numbers, and so I, made a transition to doing postgraduate degrees in mathematics, having done an undergraduate in music. And I did some quantum computing as part of my master's, and I thought, oh, that's lovely. Oh, isn't that cute? Isn't it nice that we've done that? And didn't really think anything of it until I started reading around what were then the plans for NIST to do their post-quantum process. And I was like, oh, there's something important here, maybe. And so I started reading more and went back to textbooks, went back to reading papers, but now more broadly, not just in mathematics and other things I was interested in, but also in quantum computing and quantum information theory. My background, my postgraduate studies were in information theory from an algorithmic point of view. So randomness for Martin-Löf randomness and computability theory in particular. So it was very natural and very easy to make that transition, and certain concepts like, oh, this is Turing complete or this is Turing universal were like, okay, cool. I didn't have to do any more reading on that. So it felt very natural to read about it and to try and get my head around, the quantum advantage stuff, which was really interesting and really fascinating. And having a background in cybersecurity as well, I was a pen tester for a while, and then working in a cybersecurity research capacity, I was like, oh, there's a lot of relevancy suddenly, and there's a lot of things that I should be, talking about and looking at doing. So I kind of grew into it sort of through cybersecurity, through just being a bit hacky with the way I interact with technology and just being really curious. It just sounds so cool. Everything part of quantum tech sounds so cool. First quantum revolution was like lasers. It's just like, there's nothing cooler than lasers. So now there's space and all that. So it was kind of from the appeal of like my inner sort of sci-fi sort of leaning, and then from just studying and reading and seeing how I felt about things, and then quite naturally it got involved in my work. And so since the NIST process has been rolling, I've been reading up on it, keeping tabs on it, and now I'm more or less moving into a very quantum-oriented sort of headspace and professional space.
Yeah, so we have a lot of overlap in our past. I did the whole hacking thing for many years too. I've been going to DEF CON since I think 2000 or so. I've been going there quite a long time.
It's great.
Yeah, it's amazing. So you're here representing Quantum Village.
I am.
Let's talk a little bit about DEF CON for those who don't know. I think this could be a fun answer. How would you describe DEF CON to someone who's never been?
How would you describe DEF CON? So 25,000 of the world's finest hackers descend upon Las Vegas once a year, and they do two things. They talk to each other very technically, and they go to parties. And now there's more than just DEF CON. There's Black Hat, and there's B-Sides Las Vegas that take place. And it's all just a kind of a meeting point. It's affectionately known as the Hacker Summer Camp. So Quantum Village itself is born from that kind of ethos and is kind of born from that space. For those who've never heard of DEF CON, they've probably never heard of the villages. So there are lots of what you'd normally call special interest groups. So there's a car hacking village, and every year they bring 2 or 3 Teslas, Fords, Dodges, whatever, and you can hack them. You can take them apart. You can go, I want to see what this thing does. And they'll give you a screwdriver and go, here you go and tell us. And so, it's stuff that doesn't necessarily fit into the main tracks. Like it might be a little specialist, or it might, there might be like a run of talks about the same manufacturer. Tesla's are very popular. Ford's very popular. And then there's quite a few of these. I think there's like 35 now. There's Misinformation Village, there's an AI Village, and now there's a Quantum Village. So what we're trying to do is bring quantum tech to 25,000 hackers in Las Vegas. We did it last year, and it was a lot of fun. We were really successful, and we're looking to do it again this year as well.
Yeah, so for anyone who hasn't been there, it's a huge show. There's there's 3 gigantic rooms or so, 3 or 4, and I mean like really big. You feel like you're at a concert or something. That's how big they are. and
nice conference buildings, yeah.
Yeah, and you're watching these big talks. I gave a talk there. I gave a talk at DEF CON 25 on hacking smart contracts, and it's a big fun party, and you get your shot of whiskey or whatever when you first go on as a speaker. So that loosens everyone up immediately. But then, yeah, these villages or these like kind of offshoots, you go down the hall, you sometimes to a different building, and there's these rooms where there's other tracks of talks going and activities, like you said. So Quantum Village is one of those, and it's a new one. And I expect it's going to grow in popularity because, I mean, hey, I'm a champion of this industry, so I'm certain of it. I'm positive it's going to grow.
There we go. It's been said now. You have to come.
Yeah. We're going to be doing some stuff there, I'm sure. So, and then you do this, and then also, I mean, you work as, I guess, still in sort of a hacker role, right? At like a global bank too. We'll just leave it at that.
So I do, yeah. So I do sort of, at the moment, more mathsy cybersecurity research. I've done reverse engineering. I had a time when I was specializing in hardware hacking, so reverse engineering microchips and extracting cryptography keys, for example, like a bit of a party trick. Before it was kind of this, it's now a much more done thing than it used to be, which is really good because it means that, you're getting more eyes, more people looking at these things. And as long as you have a responsive view, an active take on security, then you're going to naturally be able to try and improve that. And so that's where we took the view for Quantum Village. My co-founder, Victoria, and I took this view of trying to be more pragmatic and more forward-looking and not just go, quantum's going to ruin the world, it's going to break all cryptography in 2 months or 2 years or 20 years or, whatever the estimates might be. We want to be more pragmatic about it and go, okay, well, what does that mean? What does it mean to compute something in a quantum space? And how does that affect notions of, for example, privacy or computational cost and offsets, and how's that going to affect things? We call that project Quantum Life. So what's our lives going to look like? And some people might say, well, why do you care? Who cares? And that's a perfectly valid point. Maybe nobody cares, but maybe everybody at some point might care. And I think we've learned so much from previous technical revolutions, various bubbles and various tech developments, that we can sort of go, okay, this worked, and this didn't work. This was a bad idea. And can we apply that kind of looking ahead by considering what's gone before to quantum? And so that's where our activities lie. We run competitions like the world's first quantum capture the flag. So rather than having a hackathon, we managed to get a sponsor together to run a quantum capture the flag where you had challenges. So my favorite was that you had a picture round. So it was designed for every level. There were some very in-depth quantum challenges. And then there was a picture round because it was kind of fun. And who's this? It's Peter Shaw. And yes, you can reverse search it on Google. That's fine. But we would still try and trip you up. So who's this? And it's Kitaev. But you had to put his name in Cyrillic to get the points. And so it's having fun with it. It's being a bit adventurous, being a little bit sort of poking what could be and what might be, and trying to draw out, the interest in quantum tech that certainly I've developed and my co-founder has developed, and this way of looking at technology that is very sane and very practical, but also getting excited about it. There's a lot to be excited about, as well as potential doom and gloom.
Mm-hmm. Do you find that you're bringing some of this quantum to your day job then? Or you're trying to push the issue at work?
Very much so. And as the investment's gone up, so has the interest in quantum. As one competitor picks it up, maybe we should have a look at this. As other people start looking at, well, we've got this post-quantum competition. And I think for a while, people were a little bit, oh, they'll fix it. It'll be fine. And then you started having things like, a site being broken in a weekend over a laptop, and it's like, oh, that's bad. Oh, dear. And so we're kind of realizing a lot of things that we didn't really think about when it comes to cryptography in particular, from a defense point of view. And the future being really crypto agility. The problem isn't the quantum computers, like they're just sitting there being very cold or very empty or both, then doing their thing and being very cool or super cool. Whereas what we're trying to do is sort of go, well, the fact that I can't easily swap out a particular cipher or particular piece of cryptography very easily means that I am going to be caught up in a very lengthy process only to find out maybe on Friday, I have to do it all over again because, some very talented researcher somewhere has worked out how to do it on a potato. So the way that we're trying to sort of approach it is pragmatic. And there's a lot of benefits as well. This is what we want to communicate. It isn't just, everything's terrible. The world's going to be in flames. It's all going to be downhill from here. There's a lot of opportunity as well. And that's kind of where some of our more research activities have come about, where, we're publishing certainly their own preprints. They've been submitted to journals, trying to build into a narrative of quantum is as much a threat as it is, just generally a tool. And so we can really go, okay, can we utilize this tool to help us solve problems in cybersecurity? Not just use it, not just fall victim to quantum crime, effectively, but really sort of go for, okay, suppose you were a talented whatever, how would you develop a solution that would blend this in? What are the problems that we're facing now in cybersecurity beyond just post-quantum cryptography? To be able to go, okay, here's a use case where we can go, right, let's fix this with quantum.
Yeah, and I've been saying this for a while, that the use cases are going to come way before the crypto threat's going to happen. These machines are getting more powerful. We're looking to find things. So what's interesting here is, everyone knows about that quantum threat to cryptography. You're considering, and my team's been considering this too, different ways we can use these machines to help the InfoSec world. So like right now we're working on one to try and help detect indicators of compromise better, with binary classification. And I wanted to have you come on also to talk about the paper you wrote, which I thought was pretty cool.
Thank you.
It's called Cutting Medusa's Path, Tackling Kill Chains with Quantum Computing. And first of all, hey, great job giving it a DEF CON-like title. Like normally scientific papers are a little dry in their titling. I know mine are.
Gotta have some.
Yeah, so it's pretty awesome. So I'd love to talk a little bit about that, to try and explain, first of all, to readers what kill chains are, I guess is a way to start
sure.
in general in InfoSec.
So a kill chain is probably the most unfortunate sequence of events you could imagine on a cybersecurity point of view on a network. So a kill chain is when you go from being like any other user, say accessing a website or connecting to a Wi-Fi or whatever, and there's a sequence of events because of not just vulnerabilities, but also misconfigurations, lack of segregation, common network issues that usually do get identified and maybe not fixed. Maybe they do. I'll come to that later. But you have a sequence of unfortunate events that leads you to some kind of significant control over, say, a network. So in case of a Windows network, which quite a few people might be familiar with, it would be a sequence of events where you start with connecting to a website, connecting to a Wi-Fi, something similar to that, and ending up with domain admin. So complete cyber control of a network. All the users, all of the IP, all the data, the databases, the financial stuff, everything is controlled by that. So that is what's meant by a kill chain, as in you've kind of gone in for the kill. And so you've arrived at that point that you've attained what you might refer to as an unreasonable level of control. And that's when, if it gets discovered and gets leaked, say, to the press, that's when you get like headlines, like sort of, this company was hacked and that kind of thing. So that's a kill chain. And that's something that is a very hot topic in terms of both on the attacking side, finding them, and on the defensive side, preventing them. And so you'll see lots of solutions talk about kill chains in your network, in your supply chain now is a hot topic as well, because a lot of these things are very well interconnected. So a lot of people are now realizing, okay, we need to have this more holistic view in order to be able to attain knowledge of, okay, here's our kill chain and here's how we're going to fix it. And then rinse repeat for all kill chains is currently the thought. So that's what a kill chain kind of is, as broadly as I think I can put it.
Yeah. So traditionally you would do some kind of vulnerability assessment, pen test, whatever. And then you would have all these vulnerabilities that you identify. And then you would have to figure out what's the sequence of events that could lead to the worst outcome. And you really got to fix that first, right? I mean, is that simplifying it enough? So what part of that process did you want to improve with quantum computing?
So what we were looking at was the notion that first occurred to me, I think it was at a bar speaking to a CISO who's a friend of mine at another financial institution quite a few years ago, actually. And we kind of arrived at the conclusion that a lot of cybersecurity is about to become a data problem. And actually, I think in the ensuing years, a lot of it has become a data problem. And where you have data problems, you have chances to apply optimization. And you have very hard problems that have lots of combinatorial strength, to put it mathematically. To put it more simply, things that have lots and lots of options that grow exponentially as you start, sort of traversing these various paths through a network. And so we wanted to try and see, is there a way that you could maybe not just tackle certain kill chains, but tackle as many as possible by looking at the graph, as in network graph connectivity of issues. Because obviously, if you're going to have a kill chain, each step has to have some kind of visibility on the next step. Otherwise, it doesn't work.
Yeah.
So we wanted to try and see if there was a way, or what problems we could look at. And something that's a very old problem is the problem of patching, often referred to as patch analysis. So patch analysis is a slightly broader term. It includes things like being able to go, yes, this patch won't bring down production, we hope, we think, we're 90% sure. It's the ability to go, this patch is really important. There are things called CVSS scores, which is literally a 0 to 10 or 1 to 10 for, if it's 1 to 4, it's not a problem. It's okay. It's like, you should fix it, but there's other things probably. And if it's a 10 out of 10 or 9 out of 10, it's okay, you're coming in this weekend, please, because we need to fix this. So you've got this whole vast scale of potential issues, and it's a lot of data. And a lot of companies now, having done thousands of days of pen tests and written hundreds of reports, I've generated a lot of data for customers, and now they're getting it basically live. Yeah, you have providers such as Tenable or Qualys who have active scanning regimes where they will just pipe you data all the time, coming in from various detectors and sensors and scanners and all the other stuff that they run. So you've got all this data, and it's great. You know where all your problems are. But that's now like just an infinite to-do list, potentially. And that's a problem. And knowing what kill chains affect what is one way of doing it. But the problem with that is that kill chains are, I don't want to say they're Turing complete, but they're pretty close. As in, there's lots of different ways of enumerating different problems and putting them together. And hackers are very good at doing that. But the hacker only has to be right once, whereas the defense team can only be wrong once and they get hacked. Whereas the attacker can keep going and keep trying and changing IPs and routing themselves around the world. So there's this huge kind of inequality when it comes to how much success is required to prevent a massive problem. So we looked at this problem of patch analysis from that view. And what we found was there's a really good way of representing that as a network graph problem. And once we had that, it was like, oh, maybe we can apply quantum to that in some way, shape, or form. And so that's how the paper began.
Okay. So that step of the problem that you were trying to solve, how did it compare to the classical approach? I'm assuming you want to share some benchmarking ideas here.
Yeah. So the possible ways of getting around a network start growing exponentially when you start tracking more than 3 or 4 layers of kill chain. I've popped kill chains that have been 5, 6, 7, 10 layers deep, where I've had to really work a way around the network and rely on things that people don't normally think of, like stealing entire browser sessions from users I can connect to, or because I could get a joint local admin access, which is a very common network misconfiguration, for example. But in order to get to that point, I had to get onto the network where it was locked down with segregation. I had to work out how to flip around. And so you're always flipping between software vulnerabilities, misconfigurations, library issues, or just, human error, like a really bad password that nobody noticed. And it doesn't really matter whether that password, none of your staff on the network noticed. If the hacker notices it and it happens to be, say, password 1, ! Because that's secure, then, you suddenly have a problem and you might not have even detected that. So the way we were looking at it was much more to go, okay, what kind of graph problems could give you an ample coverage from, thinking that maybe there was a quantum speedup, not necessarily focusing on one, but going, how would you fix it all? And the problems become things like the one that we used was a minimum vertex cover. So that's the mathematical name. But basically, it's the minimum number of nodes you need to remove so that every edge disappears. And that is how you remove every kill chain, obviously, because if there's no edges, there's no traversal. If there's no traversal, there's no kill chain. So that would be like that. We went, okay, that's the extreme example. That's the logical conclusion. So you just do that. And then you try to start looking at how easy it is to compute. So you might set up some NetworkX Python sort of environment and go, okay, 10 nodes. How does that work? So depending on the density of the graph, like sort of it's either quite straightforward and very quick, or it takes a few seconds. And then you add a node and it takes quite a few more seconds. And then at some point you add a node and it goes from taking a few dozen seconds to a few minutes. And then it takes tens of minutes by just adding a node each time. And by the time you get up to, say, 30 or 40 nodes, you're waiting quite some time. And every one you're adding is adding even more complexity that has to be taken into account to find the cover. And this works both whether you use the exact algorithms or an approximation. There's lots of approximation algorithms you can use as well, which give you they give you a good enough job. It might not be perfectly minimum, but it's a vertex cover. And that's probably enough. But again, all that does is kick the can down the road. They start getting longer and longer when you start getting past nodes and graphs of, I think sort of when you get past 100, it's like, yeah, I'm just going to go and make a coffee and dinner.
And go to bed.
Loads of time.
Yeah, and see you tomorrow, really.
Yeah, pretty much.
Yeah.
And so that's where you start getting the complexity sort of really exploding. And that's where we looked to see if there was a way of going, okay, I've heard that there are these quantum variants that can be solved quite quickly. And so we assessed various ways of doing that. So that was kind of how we got to the point of going, right, now let's try quantum.
Okay, so in as simple as way as possible, what would you say your results are for listeners to understand? So
we basically found that we presented a paper which basically shows you that there is a potential for a quantum optimization on these problems. We use a D-Wave, so not using a universal quantum computer, we use a D-Wave because they're a lot bigger, there's more qubits, and the kind of problem we're trying to look at is one that fits very well onto a quantum annealer. So the first stage was to go, okay, let's go and try for that. The next stage was to then go through and recode the data. So the problem with vulnerability data in particular is, one, there's no real publicly available data set. So had to make a few little guesses there, but I went with my experience and I formulated an idea that you have two main data points. You have vulnerabilities and you have hosts. And for anyone who's done some graph theory, they might go, oh, that might be a bipartite graph, which in simple terms is just a graph with two sides. So you take one side as the hosts, and then for every host, you attach it to the other side, which is representing vulnerabilities. So the data you get is usually host first, but your questions are vulnerability first. So there's a validation in that you actually should use graph structures to get your vulnerability data stored and utilized, because you tend to say, oh, okay, this host has these issues, and this host has these issues, and this host has all of these, and then move on from there. Whereas the questions are, okay, we've just read a headline that says that this issue is a major problem. where are all the hosts with that? And if you don't use a graph, you have to go through every single host record every time you want to ask a question and look for the thing you're looking for, which is, it means that you have to go to the database every single time, which means it's very slow. Even with well-indexed databases, it just doesn't really help all that much. So moving to graphs was very natural, but the bipartite graphs don't fit too easily into the problem we wanted to solve, which was a fairly nice, neat quadratic unconstrained binary optimization, a QUBO, which is what we really wanted to use. And that's where we went on for the annealer. So the idea of getting to that point was to do a transformation. And that's where I think there's the interesting idea from a mathematical point of view in the paper, which is there's this nice way of coding these things, which, if it applies to your problem, allows you to solve certain cuts on the bipartite graph by finding a total minimum vector cover on the dual graph, the graph you generate from the bipartite graph. And that doesn't take much more processing overhead. It's you just iterate around the whole graph and construct the second graph, and then you solve that. So we kind of organically grew towards this idea of being able to go, okay, here's a gnarly problem. Let's look at this subset, vulnerabilities and hosts. And we're going to try and remove kill chains. So what's a kill chain then? A kill chain is when two vulnerabilities are connected by a host.
Yeah.
Then we took that problem and went, so we'll make another graph that connects vulnerabilities if and only if they're connected via a host. That was easy enough to do. And then when you solve that, we wrote a short proof which just says, okay, if you remove all the edges here, you totally disconnect all of the vulnerabilities from each other on your original bipartite graph. And with that, you're then able to say, okay, I haven't fixed every patch because that's a really hard problem. But what I have done is I've removed all of the well-connected patches. So there's no kill chain here because literally no vulnerability can see any other vulnerability. And that's the kind of totality which you're able to gain. And that's an exponentially hard problem as the graphs grow. But with a quantum computer, the line stayed pretty flat when we were measuring time.
Yeah, that was like pretty much the most noticeable result that should make people's eyes open up. Because with a really large corporation, this could be monstrous, like to try and do.
It grows really, really fast. And there was a part of adjusting the density of the graphs we were testing with. So I would just generate random graphs and test them with the algorithm and generate the graph, send it to a D-Wave, solve it classically as well. And I noticed, the classical solver was very quick for very small graphs, and the D-Wave was always taking this time. We were going to wait in the cloud queue and go around and come back. And then by the end of it, for lower density graphs, the D-Wave was coming back in a very short order of time with completely correct results that were almost identical to the classical version. Except that the classical version had done all this extra work, and the D-Wave, hadn't. It had just gone, is the answer to your QUBO in 33 variables, sir? And I was like, thank you very much.
Yeah, so that's a pretty consistent choice then. We see this a lot with D-Wave lately. People are just picking it for things because it's giving that kind of like same performance. And this kind of problem doesn't have the normal bottlenecks that people worry about with quantum. Like this isn't 24/7 real-time requirement. You don't run this all the time.
No.
This would be like something you'd run every once in a while. You'd figure out that first layer, and then you go to the normal CVSS order. Fix your highs within 30 days, your mediums in a couple months, and then your lows in whenever, 6 months.
Whenever you can.
Yeah.
The next thing is that any low that appears on your minimum vertex cover graph, the output from this algorithm, any low that appears there is really well connected. And that's what you can say. So actually, you should fix the lows on that first before looking at the other ones. Because
you would fix the kill chains, and then you would go through the order as time allows. Yeah,
exactly. And so
this could be huge.
Yeah, so it lets you take the sprawling problem where every machine is giving you, a bad day, multiply that by, tens of thousands, hundreds of thousands for some organizations. And you can take that down to, okay, here's a memorandum, put it out there, please fix these 10, these 20. And okay, you're not going to remove all the kill chains even there, but because it's a minimum cover, and I did a weighted version of the algorithm as well, which works quite nicely, you can actually go through and say, right, here's the things that are really well connected. So these will appear on the most kill chains, but you're doing it without having to make a decision about an idea of what's called betweenness. You're doing this without having to make an idea of centrality notional. So for those who don't know, there's a thing called centrality in graph theory, which is to say there is one node that is in some sense in the middle of these networks. But depending on which one you choose, you get a different answer each time. There's a really famous example, I think, from 2010, which is there's a graph where depending on which centrality algorithm you choose, it gives you a different node every time, no matter what. So it's a contrived example, but it means that you've made some kind of assumption there. Whereas here, we're just going, no. If it sits between something, it gets removed according to, the weights and its own CVSS scoring. So it lets you be a lot more proactive from a kind of blanket defense point of view without having to, churn through imagining what could an attacker do here? What can an attacker do over there? Or spending, infinite money on pen tests, which is the other way of doing it, right? I just keep spending on pen tests and let the hackers tell you everything.
Plenty of companies who are fine with that on both sides.
True.
Yeah. So I wanted to, since we're talking so much about security and quantum, I figured it'd be a good time to just bring up that paper. You and I already talked about this a bit, but yeah. So over the holiday break, a Chinese paper came out that they basically claim to, it's called Factoring Integers with Sublinear Resources on a Superconducting Quantum Processor. And they claim that if you extrapolate from the work they did on 10 qubits or so, it should be possible to crack 2048-bit RSA with 372 qubits. And this is, of course, building on some of the work from that infamous Schnorr paper, not to be confused with Shor, that everyone was talking about a while back. So yes. I thought you might want to maybe share a thought or two on this.
I think it's really interesting looking at the reactions more than anything else. The paper itself, self-contained, it's, I read it and I was like, yeah, this seems correct. And it was when you pay attention to what isn't there, and I think this is what Scott Aronson and Peter Shaw himself pointed out, is that it doesn't really tell you how long the circuits are going to be. So there's this kind of analog, for want of a better pun, there's this kind of analog for time memory trade-off when you talk about a circuit, which is you can take the depth and width of a circuit, number of qubits and number of gates being depth. You can take that and you can adjust things a little bit, and you can usually trade off one for another. You can kind of make things work on fewer qubits, but you have to do more gates and more resets and do more with the quantum computer while you have it. They don't really talk about the gate depth, and they use QAOA, which is almost notorious at this point for having very hard to pin down estimates for actual advantage. And even the algorithm itself, Schnorr's algorithm, does a lot of work outside of the thing that they've optimized, which is just one of the harder parts of it, which is this Babai's algorithm section. They've kind of gone, well, we're going to do this, but there's always the chance that the Babai algorithm is already too close, and so your annealer might not actually get to the ground state necessarily for various reasons. So I think that you've got not just your annealer, your quantum QAOA.
Yeah. Yes.
But you might not necessarily find the ground state of that Hamiltonian. So the fact that you can do it on 10 qubits is kind of cool, I think. I think it's a nice sort of idea, like sort of you can do it with minimal resources. That's kind of fun as an idea. But in terms of its usefulness, I don't know. I'm not convinced that it's going to really add much to that, because there's so much that still has to happen on those 370 odd qubits to make them last long enough, to make them stable enough that you could actually get a meaningful result. And then, of course, you've got to run it so many times to get because it's a random vector input. So you have to run it so many times to be able to get anywhere near a stable result. So there's a lot of ifs and buts. And they do document quite a bit of this in the paper. Just
the
not
gate depths too, like 1100 gate depth or something for RSA.
Yeah, exactly. The in-depth bits are more in the addendum part of the paper, which is the 24 pages of linkings. That's where most of the caveats are. Less so in the leader. So it's just, I think, a little pushy maybe.
When you hit that first conclusion, they even have a line in there. I pulled it out just to bring up. It says, it should be pointed out that the quantum speedup of the algorithm is unclear due to the ambiguous convergence of QAOA. It's like, that's a really big word. I mean, when you're talking about thousands of days or, whatever to run it, millions of years, I don't know.
Exactly. And I think there's a misnomer. What they've really shown is that you don't necessarily need hundreds of qubits. But you also don't necessarily need a quantum computer. My CPU will factor numbers just fine. I can factor numbers on an Arduino 8-bit microcontroller. 8 bits are enough. Mm-hmm. But that's kind of not the point.
Yeah. There's other factors.
Yeah, there's other things to do first. So I think that, I like some of the work that's there. I think there's some really nice ideas in the paper. I don't want to just say this is rubbish, because I think the hype around it is a bit rubbish. But I think the paper itself has got some cool ideas. It's a nice way of going, okay, here's how we can slot these things together. But is RSA broken in the near term on NISQ quantum computers? I think we're probably okay, modulo some very fancy engineering or a lot of work on the algorithm side itself to really reduce the depth of the circuit as well as just putting on 10 qubits.
Yeah, I mean, it could be a start of something scary. It could be. We'll see. But yeah, there have been some headlines like a month ago or so, creating a black hole, a wormhole. That's not at all what happened.
No, I think Preskill described it as a nice alternative description, which is very close to saying it was an alternative fact, I think. It wasn't necessarily, it was cool, but it's like, we call it magnetic spin because the equations look similar to spinning a basketball on your finger or something.
Yeah. I mean, it was just a two-dimensional representation of a, multi-dimensional wormhole, so it doesn't really do the same thing.
No.
Yeah.
And there's, as a mathematician, I can tell you, there's a lot of stuff in topology and in algebraic geometry of various dimensions that, things really do change between 2 and 3 dimensions, 3 and 4 dimensions. Mm-hmm. There are some things which are totally unsolved in 4 dimensions, but solved 5 and above, and 1 to 3. Just in the 4-dimensional case, we've got no idea. And it happens to be we're in what is probably largely a 4-dimensional space-time. So there's plenty of questions that we can ask still. I don't think we've quite eradicated ourselves out. I think it was an interesting paper, but I don't think it was I think the phrase sublinear resources is the thing I would change. A sublinear width or depth, or a width of qubits maybe better.
So we danced around on some stuff here. I don't know if we're going to see any wormholes at Quantum Village this summer, but I think we are going to try and do some cool things. I want to have you come back with your co-founder, Victoria, and we can have a chat as we get closer to the show, because I think it's going to be worthwhile to let everyone know what's coming. Is there anything you want to tease right now before we sign off? Any ideas you have for the summer yet?
So we've got lots of ideas which we want to sort of put out there sort of slowly. We've got some ideas so we released the first embedded quantum simulator, which meant that you could hold a quantum computer in your hand, which is kind of fun. And we've got ideas for a badge. So it's going to be a little circuit board that you can wear. It'll have a little battery. It'll have Wi-Fi.
Oh, that's dangerous at DEF CON.
That's the most fun you can have at DEF CON, I think. So. And we're looking at doing a very cool, developing some very cool software for it to do with quantum networking, and also to do with a quantum art project, which is still very hush-hush, but we're working with some really cool people to help that. So if people want to get involved, they can come and have a look at our Slack or our website, quantumvillage.org is that one. We'd love to hear from people. The Discord is really active, actually, for what you might consider a really niche Discord, like sort of it's quantum tech, but, from hackers and security perspective. But we have a lot of really interested people. So we're going to try and do it again we're going to try and bring lots of cool things to both the CTF and to DEF CON. So if you want to hear more or want to get involved, they can contact us over social media, over our website. There's loads of ways for them to come and get involved.
Yeah, I'll put that in the show notes. And I'm going to be pretty much living there for a couple of days in the summer. So we're going to have a lot of fun. I can't wait to see you in person again.
Absolutely. It was really interesting. Like, first year we ran last year, like, we didn't know what to expect. Are we going to get eggs thrown at us? Are they going to go, this is nonsense? We had no idea, but people loved it. People camped out. They canceled all their other plans and stayed at QV. And we had some really interesting sponsors. We had exclusive time on Oxford Quantum Circuits Lucy arranged. We had really cool talks from people at Quantinuum and Sandbox and Quintessence Labs, some really nice ideas about quantum machine learning, talking about this quantum life. And people really connected with it in a way that we just didn't anticipate. When we ran the Capture the Flag, of the 5 people who won, only one, and not the guy who came first, only one had ever actually written a quantum circuit before.
That's amazing, yeah.
And this was really cool. So, we're always open to people who want to come and help out or even sponsor, but we're always open to having people connect with us and sort of take part. Like, we're really open to just helping people lift that quantum literacy.
Sounds great. Yeah, I can't wait. It's going to be quite a party.
I think so. Well, we have a party planned as well, but more on that later.
So thanks so much for joining, and I'll be seeing you soon. Definitely.
Absolutely. Thank you so much.
Now it's time for Coherence, the Quantum Executive Summary, where I take a moment to highlight some of the business impacts we discussed today, in case things got too nerdy at times. Let's recap. Mark created the Quantum Village to bring quantum curiosity to the infamous DEF CON hacking conference. Participants can learn from talks, sure, but can also participate in quantum capture the flag contests and other hands-on aspects that make hacker conferences so much fun. It turns out that quantum computing might have a few uses in the InfoSec community too. Mark's paper, linked in the show notes, shows one way quantum can help solve a problem faced by organizations dealing with the remediation phase of a vulnerability assessment or penetration test. How do you prioritize fixing what could be hundreds or thousands of vulnerabilities? Before you resort to the old rule of fixing issues ranked high, then medium, then low, it makes sense to fix the vulnerabilities in all categories that could lead to a kill chain or path to exploitation. Trying to prioritize these with classical computing can quickly become challenging. The more nodes you add, the more exponentially runtime can go up in solving for the targets that need patching. Mark's approach uses D-Wave and a QUBO to solve the problem, and remarkably, it stays flat as far as the required runtime with increasing nodes. Think of what we're all hoping for with speedups in quantum use cases. We want to go from classical processes that run overnight, say, to quantum ones that complete within an hour while we're answering emails in the morning. This experiment shows hope for this type of use case in information security. When is the overall threat to encryption coming? The first date everyone has to worry about is when NIST publishes its final post-quantum cryptography standards, possibly within a year or so. Regulators will come knocking when this occurs, and those in cybersecurity will have to have a plan for moving to post-quantum ciphers. A recent paper from Chinese researchers seems to warn of factoring numbers sooner than the 4,000 error-corrected qubits we're waiting for. They claim as few as 372 qubits in a noisy NISQ machine will be able to decrypt RSA 2048. However, the quantum approximate optimization algorithm, or QAOA speedup involved, is unclear, meaning it might take just as long as a classical system for all we know. Future experimentation will tell if the new approach leads to anything promising, or shall we say, threatening? That does it for this episode. Thanks to Mark Carney for joining to discuss stopping kill chains with a quantum computer and the Quantum Village. And thank you for listening. If you enjoyed the show, please subscribe to Protivity's The Post-Quantum World, and maybe leave a review to help others find us. Be sure to follow me on Twitter and Instagram at ConstantHacker. That's Constant with a K, Hacker. You'll find links there to what we're doing in quantum computing services at Protivity. You can also DM me questions or suggestions for what you'd like to hear on the show. For more information on our quantum services, Check out Protiviti.com or follow Protiviti Tech on Twitter and LinkedIn. Until next time, be kind and stay quantum curious.